So power converters can be required for different applications. We have some different applications starting from adjustable speed drives, so hybrid or electric vehicles, flexible AC transmission systems, custom power devices, which will use to enhance the power quality, active power filters, so renewable energy integration, generation, and HVDC and HVDC plus, so grid connected applications, transformerless applications, battery chargers, and home applications. So all these things, the power converter is necessary. So these power converters can be broadly classified into different types. So one is the direct conversion, so which is AC to AC conversion. So we have two options are there. So one is the matrix converter, and the other one is the cycler converter. So this cycler converters uses thyristors. So where is this matrix converter, which uses the self-commutated devices. So generally, this is the direct conversion. So there are disadvantages with this one. So this cycler converters, you cannot control the huge range of frequencies, especially when you are operating with high-speed electric drives, for example. So these cycler converters are not preferred. So this especially, so when you are operating with low-speed drives, maybe in the 100 RPM, 200 RPM, 300 RPM range. So in that case, the cycler converters may be suitable. Matrix converter, so which is having good advantages. So but the thing is that so matrix converters, the failure rate is exceptionally high because the short circuit of two phase legs, so it's very common in matrix converters. We have to take all these necessary precautions. So when you're using this converter, and moreover, when matrix converter that also require huge number of switches. So next we have this indirect conversion. So in this indirect conversion, so we have this AC is converted to DC and this converted back to AC with variable frequency and magnitude. So we have two options are there. So one is the voltage source approach and the current source approach. In case of current source approach, so again, it may be operated in PWM current source inverter, so that is operating with self-commutated devices, or it may be operated with line commutated inverter. So this will operate with line commutated inverters either with with thyristors, or sometimes it may be operated with GTOs. In case of voltage source approach, right, so we have several options are there. So one is the two-level inverter. So that what we studied in previous classes, that is two-level voltage source inverter. Right. So next option we have multipulse inverters. So this is an extension of two-level inverters. By combining multiple two-level inverters, we can obtain a multipulse output. So next we have multi-level inverters. Multi-level inverters, we have several topologies are there, starting from flying capacitor, neutral point clamp, cascade edge bridge. So these are the fundamental or the basic topologies. So with these topologies, so other few inverter topologies are derived. So we have a separate discussion on this current source inverter in later classes. So how this PWM source inverters and this load commutated inverters are actually working, that we will discuss, right? Maybe at the end of this course. So first we start with voltage source inverters. So far we discussed these two-level inverters. So now we'll start with this multipulse and multi-level inverters. So why exactly this multipulse and multi-level inverters are used? So that we'll discuss now. So why exactly we use this multipulse inverters or multi-level inverters? The first thing is that to increase the power levels. To increase the power levels. Right. So why we need to increase the power levels? For example, if you want to drive a large motor in the range of 100 kilowatt range or 1 MVA range, so in that case, if you use the two-level inverter, right? For example, if you use the two-level inverter, so how it will be in case of a large machines. So let us assume that this load is some large electric drive, right? Say for example this rating is 3.3 kV, for example. So still you are preferring to use a two-level inverter, right? So how much DC voltage you required to obtain a 3.3 kV? How much DC voltage you required? This 3.3 kV is the line voltage RMS, right? So how much you require? So how much you require?
3.3 by 0.9.
Why 0.9? So we studied, right, if MA equal to 1, if you use sine PWM technique, right?
0.618.
So how much you require? So this is 3300 divided by 0.612. So how much this is?
5.39.
5.39, roughly 5.4 kilovolts, right? So roughly 5.4 kilovolts. Okay. So now tell me, so what is the blocking voltage? For example, if you use, so this one, so it is 5.4 kilovolt, right? So here you are getting a 3.3 kV line voltage RMS value. So what is the blocking voltage of this device? So how to measure the blocking voltage? How to measure the blocking voltage or the peak inverse voltage? So for this particular switch, right, so these two switches are complementary, right? If this switch is off and this switch is on, so what is the voltage across that switch? Let us assume that this voltage is VDC. So what is the voltage across this particular switch?
VDC.
Switch.
It is
This voltage is VDC, right? Okay. So that is how the blocking voltage is measured. The voltage across a particular, or the maximum voltage across a switch. So when it is not conducting, or when it is in reverse bias, or when it is not in conduction, that is the maximum voltage that appear across a particular device. So this is also known as peak inverse voltage. Peak inverse voltage. Inverse means the voltage that appeared in the opposite direction. So that means each switch is supposed to withstand VDC voltage. So these all the switches are supposed to withstand VDC voltage, that is 5.4 kV. So that is the minimum or the bare minimum voltage that is required. But we have some factor of safety. Right, we have some factor of safety will be there. So usually this factor of safety will vary from 1.6 or 1.7 times to 2 times. 1.6 to 2 times, right? So how much if you consider 2 times is the factor of safety, for example, so it will be 10.8 kilovolts, right? Or for example, if you consider 1.6, if you consider 1.6, so in that case, so it will be roughly 8.6 kilovolts. 8.6, right? So it must be ranges from 8.6 kilovolts to 10 kilovolts. So that means the switch must withstand somewhere between 8.6 kilovolts to 10.8 kilovolts. So such kind of switch you need to select. So remember, for power electronic devices, unlike machines, right, so there is no overrating. For example, in case of machines, if it is rated for 10 amperes, right, so slightly it can, for example, if the load is 1 per unit, if you increase the load by 10% or 15%, so maybe the current increases, but still, so there is no much damage to the machine. So even though if it is allowing for 10% margin of even though it is running for some reasonably good amount of time. But unlike these machines, in case of this power electronics, if it is rated for example, the rate is for 1.2 kV, so in that case, so for slight variation, maybe for 5 seconds or 7 seconds, even though the voltage is exceeds that, so the device may be failed. So it will not comes with over voltage rating. So we have transient voltage rating will be there. So that may be for some microsecond duration or some millisecond duration. But for sustained over voltage, it cannot withstand. If the over voltage is there for a longer duration, maybe 1 second, 2 seconds, 3 seconds, something like that. So in that case, it may not, the device may not accept that and it may be damaged. And the damage is permanent. And that particular damage is permanent. Okay. The thing is that the power electronic devices so are not comes with overloading factors. So that means if the 1.2 kV, so that is the rating is given, so you must operate so in the ranges. That means you must operate less than 1.2 kV only. So in this case, so you need to select a device which must withstand between 8.6 kV to 10.8 kV. So such kind of devices, for example, so what is current status of devices are different power semiconductor devices are there. So we have power diodes are there, thyristors, GTOs, and IGCTs, and IGBTs are there, right? So here, generally the devices are manufactured or devices fabricated. The two things in mind. So one is to increase the voltage rating. One is to increase the voltage rating of the device or increase the current rating or the current handling of the device. Okay. So that's why we have, so voltage is the parameter here and the current is the parameter here. You can see that the power diode, so which is rated for the maximum right now that is available. So we have devices up to withstand up to 8.5 kV, right, and which can carry a current of 1.2 kiloamperes. So a power diode is available with a voltage rating of 8.5 kV with a current handling capability of 1.2 kA. So both things will not simultaneously occur. So when the device is open, so that means it can withstand up to 8.5 kilovolts. And when the device is in conduction, it can allow a current of 1.2 kiloamperes. So that is its meaning. So both will not occur simultaneously. So this is voltage is the targeted one. So in case of the current is the targeted one. So we have devices there. So that is it can capable to handle 9.6 kiloampere of current, but with reduced voltage. So that is 8.5 or 1.8 kilovolts. Right. So if you keep on increasing or whatever, if you keep on increasing the voltage blocking or voltage blocking capability, so what is the thing that the on-state voltage drop will increase. So if the on-state voltage drop will increase, so that will associated with the losses. That means the conduction and switching losses, so that will increase. So this is for power diodes. In case of thyristors, so these are matured enough. So that means we have devices that are available for 12 kV devices and 1 kiloamperes current. And in case of current, right, right. So that means you have 5 kiloampere devices are there. So but they're reasonably handled, so less voltage of 400 volts. So in case of GTO, so we have 6 kilovolts, 6 kiloampere GTOs are there, and 6 kiloampere, 6 kilowatt GTOs are there. So GTOs are well matured enough because high voltage, whenever we are using a HVDC applications or some other applications, so the GTOs are preferred. So that's why, so these GTOs with high voltage and high current ratings are available. And we have other devices, so that is IGCT. So we have 10 kV 1.7 kiloamperes device is available and the current 5 kiloamperes with 4500 volts blocking capacity, IGCTs are available, right? And comes to this IGBTs, which are popular. So we have 6500 volts, so with 750 ampere current handling, so that is available with 2400 amperes with 1700 1.7 1700 volts IGBTs are available. So generally this is known as low voltage IGBT, and this is high voltage IGBT. So this is low voltage IGBT, and this is known as high voltage IGBT. So usually if you try to increase the blocking voltage of the device, the on-state voltage drop will increase. If the on-state voltage drop will increase, so that is the, if it is carrying the full amount of current, so in that case the switching losses will be increased. So that's why, so every time if you want to increase the voltage drops, they're using a different manufacturing process. So here our requirement is, in this particular case, so our requirement is 10.8.6 to 10.8, right? So our requirement is 8.6 kV to 10.8 kV. Okay, 8.6 kV to 10.8 kV. So that is our requirement, right? So if you notice that, or if you see the manufacturers, so this is the maximum voltage, so that is available, right? So now how to choose the switch? So this will not withstand this 8.6 kV or 10.8 kV. So what we have to do is we need to connect two switches in series so that the blocking voltage will be doubled. Right. If you select, for example, if you select 6 kV switches, two switches in series, right? So that will transfer around 13 kV. See, it is much higher than that. So therefore, we have to see for other options. So generally, manufacturers are providing somewhere like this: 600 volts devices will be there, 1 kV devices there, so 1.2 kV, so 2.3 kV devices are available, 3.3 kV, and 4.3 are kV devices, and some manufacturer 4.7 kV devices are there, and 6.6 or 6.5 kV devices are there, right? So these numbers may vary, so depending on the manufacturer. So these are associated with some current ratings. It may be in kiloamperes or 50, for example, low voltage devices. So these three, so usually comes with 50 ampere current range or 100 ampere current range. So whereas this one is slightly higher than maybe 500 amperes current range or even less than that. So this low voltage device are targeted for uh, low power applications. So that's why the current range is usually small. So unless it is necessary, so they will increase the current rating, right? So here, so let us assume that if you select a 3.3 kV device, if you select, so this 3.3 kV device, so how many devices are roughly required? So three devices, right? If you count three devices, it will be some, it can block up to 9.9 kV. It can block up to 9.9 kV device or 9.9 kV voltage. So that means you need to connect three IGBTs in series. You need to connect three IGBTs in series to form a single switch, and the gate pulse for all the IGBTs are same, and the gate pulse for all IGBTs are same. Okay. So come to their cost, right? So usually, so how you have to, so whenever it is for some industry, so the cost is the main parameter. So usually cost, for example, you have 3.3 kV device is there and 6.6 kV device is there, right? For example, for one applications, you supposed to block a 6.6 k, or you supposed to require a 6.6 kV device. So instead of using a single 6.6 kV device, you may prefer to use a two 3.3 kV devices. So usually this is cheaper. So when compared to this one, so when compared to these two 3.3 kV devices, right? The 6.6 kV device is usually costly. So because this is based on the new manufacturing technology, right? So that's why its cost will be at the beginning, its cost will be very high. And slow on, once its mass producing is happening, so in that case, its cost will be come down. For example, in 2000, somewhere in 2010, 10 years ago, 11 years ago, so each 1 kV device, so that is costing around roughly 10,000 each device, or in each one phase legs, that is costing around 10,000. For example, you require the device itself is costing around 10,000, including the driver circuits and all. Somewhere it is 17,000 or 18,000, right? So that is for one phase leg. So if you have three phases, so this cost will be somewhere around 54,000. So that is the minimum cost is 54,000, including the packaging, capacitors, and other coolant, heat sink, and other snubber circuit and all. So that will be roughly cost around 15,000 or even more. Right. So this is the minimum cost. Somewhere will be 70,000, including the profit of the manufacturer and other things. So that may be somewhere around 20,000 or something. So roughly they will sell for 1 lakh rupee. Okay. So now, so with this mass production, so this cost is reduced to 30,000 or even less. We order a bulk quantity, 30,000 or 35,000, like that. So that is now. So similarly, so the now the mass production is happening. So the demand is increased. So that's why. So this is happening. Similarly, the 6.6 kV device, right? So if the demand is more, so in that case, what will happen? The price will come down. So usually manufacturers, so how they will manufacture? So either so they will manufacture a single device. So this is a single devices. So this is single device. We have three terminals, right? So collector, emitter, and base. Collector, emitter, and base, right? So this is the one side, and this is the other side. So this is where we need to mount with. So this is open one. So that means it's, you can see the metal color here. So this side must be connected to the heat sink. So this must be connected to the heat sink, and there is a screw here. This is a hole here to use a screw, right? So this is a single device. It will be there. So this is a single device. So this is known as single pack, right? So here, so this one is a phase leg. So something like this. So you can see here. You can see here. This is one phase leg. This entire thing is a phase leg. So this is known as semi pack. So this is known as semi pack. So that means this will form a one phase leg. So this will form one phase leg. So we can see that this is one, two, right? This is accessible. This is accessible. This is the midpoint. Okay. So this one is the midpoint. Right. So this is a semi pack. So this means this is a collector. So it may be emitter, and this will be this will be the midpoint. So where we have connection to the A phase, B phase, C phase, like this. So that means you require only, for example, for three phase, you require three of such things. The good thing is the driver circuit is common to both, or some little bit isolation is provided between the both, and the snubber, sometimes it will share the snubber circuit if required. And another good thing is that, so this is one phase lag, right? If you want some time delay between the two devices, so inherent time delay is available, right? So by using some logic circuits, the fabrication process itself, some provide, or there internally they will provide some time delay of 1 microsecond or 2 microsecond range. So they will provide the time delay. So you need to give only one pulse. Thing is that, so you need to give only the upper pulse, maybe for example. So the lower pulse will be automatically generated with some time delay, or in other words, with some mechanism to prevent short circuit. So these are known as semi-packs. So these are known as semi-packs. And we have, this is one compute module. So this compute module, so which is a two-level inverter module. So this is a complete two-level inverter module. So it's a complete two-level inverter module. You can see here. So this is a complete two-level inverter module. Right. So these two are the DC terminals, plus minus. So these two are the DC terminals, so plus minus. So we have A phase output, B phase output, and C phase output, and these are for firing pulses. So these are for firing pulses. So this is a complete pack or a complete two-level inverter pack. Similarly, we have complete packs are available for one chopper unit or one H bridge units will be there. Complete. This is for two-level inverter, three-phase inverter. Similarly, we have one full bridge inverter modules will be there, and off bridge inverter modules will be there. So when you are having a single pack, the thing is that the size will reduce. The size will reduce, and the cost is also reduced, right? So this will cost around roughly 15,000 or 20,000 range. Right. So come to our discussion. Okay. So that means what the thing you need to understand that if you want to block a higher voltages, you need to connect several IGBTs in series, right? Similarly, to increase the current rating, so what we have to do is we need to connect several IGBTs in parallel. Several IGBTs in parallel. For example, this is this particular device is used. If the current rating is, for example, 1500 amperes, right, this can only give 750 amperes, right? So what we have to do is you have to connect another device in parallel. So you need to connect another device in parallel, right? So current rating will increased by connecting two devices or two or more devices in parallel, and the voltage rating can be increased by connecting two or more devices in series. Similarly, for DC voltage, for example, DC bus voltage will be there. So in that case also we have to use several capacitors in series to increase the DC voltage rating. So therefore, if you are using a two-level inverter for high power applications, two-level inverter for high power applications, so you need to connect several switches in series parallel. That means each device in two-level inverter so represent a series parallel connection of several switches, and the gating pulse for all the switches is same. The gating pulses for all the switches is same. So this DC also, for example, if you are filtering capacitors will be there. So this filtering, so this is also increased by connecting several capacitors in series. This is VDC. So this can be VDC by 3, VDC by 3, VDC by 3. Likewise. So even though you're doing all these things, right, you're connecting several devices in series, still it is a two-level inverter. Still it is a two-level inverter. So there is no change in the performance wise. So if the performance, so if you studied, so it will be same only. So that is a simple two-level inverter. So only thing is the difference is, so this voltage is increased. The peak voltage, for example, you are using for 6,800 volts. So this may be 6,800 volts. This is plus 6,800 volts. The harmonic spectrum is remain same. So this THD is also remain same. So everything is remain same. And another thing is that, so to make this sinusoidal, for example, if you want to make this sinusoidal, you require to connect a large capacity filters. The voltage rating is high, so eventually you need to connect the large values of L and C. So filtering requirement is also high. when this L and C are high, so in that case, the size is also increases. So you are connecting several devices in series. So that means the size of each switch will increase. The filter circuit is also, the rating of the filter circuit is also increases. So still the performance, there is no change. So performance wise, so whatever the two level inverter for low power applications or high power applications, there is no much change. Okay. And moreover, another drawback is, for example, this device is failed. For example, this device is failed. So what will happen if this particular device is failed? So what are the consequences if one device is failed? What will happen?
Voltage test increases on other two devices.
Mhm.
Remaining two just have to block more voltage.
So what if, so if IGBT is failed, right? So will it be open circuit or it will be short circuit?
Open circuit in positive current.
Circuits.
In positive current.
Will it be open circuit or short circuit?
Sir, anti-parallel diode is there for reverse current. For forward current,
So what will happen if it is open circuit and what will happen if it is short circuit? If it is open circuit, what will happen?
Open deficit.
Hmm. If it is open circuit, what will happen?
one leg will be disabled.
So this entire switch, it will be open, right? If this is open, right? So this is open means this IGBT is not conducting, right? So neither the diode will conduct nor the actual switch will conduct. So this is comes with pack only. So usually this IGBTs are what we discussed. So right. So usually this IGBT, right? So here maybe in somewhere, so mention the name here, right? So usually comes with anti-parallel diode. Okay. Sometimes the IGBTs will come like this as a single switch. Sometimes it will come as a switch, right? And sometimes it will come as a with diode. So usually when some ratings, some 24x, some 40 do something, right? So this is K22, this voltage rating 1200 volts and 50, something like this will be there. And after that they have a word like D. If the D is there means, so that comes with an anti-parallel diode. So this 1200 is for rating of the device. So this, see here, you can see here. See here, these ratings are there, right? So this 25, so this 25 is there, right? So this 25 usually with maybe for current rating, this 1250 is there, right? 1250. So maybe the voltage rating, something like that. So this is not a unique thing. So different manufacturers will follow different terms. In the name itself, they usually provide the voltage and current ratings. If it is a single switch, so if the D means it is coming with a anti-parallel diode. So this is the manufacturer name here, right? So this is trench top. So this is the manufacturing fabrication technology. We have different fabrication technologies there. So you might have studied in the APC course. So trench top, field stop, something like gate stop, and we have some IGBTs. We have generations IGBT 4, 5, 6, something like that. Means this is IGBT first generation, fourth generation IGBTs, fifth generation IGBTs, something like that. Okay. So we have different manufacturing process or fabrication process will be the trench stop, field stop, and other manufacturing will be there. Okay. So that provides that. That means if the device is failed, usually most of the cases, so that will comes with anti-parallel diode. So unless, right, some applications where you require only IGBTs itself, in that case only we have to purchase that. If this particular device is failed, so if it is open circuited, so this entire switch is open, right? This entire switch is open. Clear? For example, if this is short circuited, right? If the device is short circuited, what will happen? What will happen?
Voltage blocking will reduce.
Right. That means now the voltage blocking of this one is slightly increased, right? Okay. So this one, so which is better? So which gives you the good reliability is one of the important aspect, right? When you have power electronic devices. So how reliable your product? So which is better? Open circuit is better or short circuit is better?
Short circuit.
So short circuit is better, right? So that means still you can use this. Okay, still you can use. We have some factor of safety will be there, right? If it is one device is failed, still you can use. If your multiple devices are failed, so in that case it may be problematic. For example, you have 4, 5. If a string is there, for 10 devices are there. If one device is failed or 1 or 2 devices is failed, so in that case the burden is shared by the remaining 8 devices. Okay, so that is acceptable for a small amount of time. If it is open circuited, right? So this will completely, so this will be completely break down. So and we have to, what we have to do, we need to replace this switch. So that's why, so when you are connecting several devices in this, we have to use when the switch is open, so it must be act as a short circuit, right? So we have this IGBTs. We have normally, so we have press pack IGBTs will be there, and wire wound IGBTs will be there. Sim press pack IGBTs, the thing is that is completely pressed. That silicon layers will completely pressed, so that will be press pack IGBTs. And wire wound IGBTs, within each silicon layer, some small wire is connected. In case of wire wound IGBTs, so when the device is failed, so it will act as an open circuit. In case of press pack IGBTs, so when the device is failed, so it will act as a short circuit. Right. Sometimes, so we need to prefer this wire wound. Sometimes what will happen, so you no need to open circuit that. For example, sometimes we need to sometimes we need to open circuit the switch. So in that case, we usually prefer wire wound IGBTs. In case it must be short circuit to increase the reliability, in that case, we normally use this press pack IGBTs. So here the thing is that, so one device is failed, the failed device must be must be short circuit, so that the reliability will be increased. In the meantime, so we can replace with a newer device. Okay. So this is about two-level inverter for high power applications, and these are the drawbacks. Okay. The thing is that this is simple, but so we have a lot of problems. So the performance wise, still it acts as a two-level inverter. You require a large size filters, and the reliability is also reduced. We have several number of switches are there, right? If the switches if the number of switches are more, the probability to get failure, so that is also more, right? If you have 6 switches and now you have 18, how much you have 18 switches, right? So that means the failure mechanism is, the failure rate is increased by 3 times. So these are the drawbacks with this one. So therefore, so how to increase that? So there are several options are there. So one is the multipulse inverters or multi-level inverters. So this multipulse inverters, you might have studied in our UG level. So when you are especially studying HVDC application or HVDC transmission lines, so you might have studied about the 12 pulse converter, 24 pulse converter, and 48 pulse converter. So which is used for HVDC application? So which is preferred for HVDC application? In case of HVDC, so we normally prefer this 48 pulse converters. So how many converters are required to obtain a 48 pulse converter? How many 6 pulse converters are required to obtain a 48 pulse converter? You studied it not? Have you studied this course? HVDC transmission. I think everyone has studied this.
Yes, sir.
How many 6 pulse converters are required to realize a 48 pulse converter? It is there in APC course also, no? Have you discussed that?
Eight, sir.
8, right?
Yes, sir.
Okay. Okay, we'll discuss this one. So this is one of the important thing. So when you are using a multi-level inverter, right? So these multi-pass converters are required to study. So this is especially for multi-level inverters. So this will be acts as a front end for multiple the multi-level inverters. So we'll discuss this whenever it is required in this course. Right. So next option we have is multi-level inverters. So first we'll start with this multi-level inverters. We'll come back to this. So this basically, so how this multi-level inverters or this multi-level voltage is generated. So let us assume that so we have something like this. So some mechanism is there. So we have one DC source is there and one switch is there. So let us assume this is 0 voltage or 0 point and this is A. Right. So this is voltage between V as 0. So let us assume this switch position 1 and this switch position 2. So now the switch S is connected to A or it's connected to 1. So what is the voltage across A and 0?
CDC.
If the switch is toggled to 1, so what is the voltage between A and 0?
VDC.
So this VDC, right? So this VDC. So if this A is connected to 2, so what is voltage between A and 0?
Minus
Zero.
VDC.
0.
Why minus VDC? So this is connected here, right? We are measuring the voltage between A and 0. What is the voltage here?
0.
0, right? So if this is connected here, so this voltage is VDC. And if this is connected here, so this voltage is 0. So that means you have 0 voltage here and plus VDC voltage here. So that means it is producing 2 levels. So what is the, if this switch is connected here, right? So what is the blocking voltage of this switch? So this is VDC, right? And what is the blocking voltage of this switch? So that is also VDC.
VDC always.
Agree? In both cases, so it is VDC. Right. So now, next step, we splitted this DC source into 2. So we have VDC now, so another VDC here. Okay. So you have 3 positions now. So 1 is the midpoint of this DC, and this is 3. If this A is connected to, right, 1, so what is the voltage between VA0?
2 VDC.
So 2 VDC, right? If this A is connected to 2, what is the voltage between A and 0?
VDC.
VDC, right? If this A is connected to this 3, so what is the voltage?
0.
0. So that means it is producing 3 levels. So that means it is producing 3 levels. So now, so what is the blocking voltage of this switch to this switch? What is the blocking? How much voltage is supposed to block here?
VDC.
2 VDC.
Why 2
VDC.
VDC? So this is VDC, right? And how much voltage is supposed to block here? So between this and this. How much voltage? That is also VDC, right?
VDC only.
Okay. So even though it is rated for 2 VDC, so but each switch is rated for VDC. And moreover, it is producing 3 voltage levels. So what is the important thing is, so we must have access to this midpoint. We must have access to this midpoint. Similarly, you are increasing this one. So let us assume that we have multiple DC sources are there, right? So which is having an access to this one. Say it is 1 here, 2 here, 3, 4, 5, likewise. So if it is connected to 1, so all these 3 DC sources, so that will becomes in series, right? Agree? Agree? Right. So that means the maximum voltage can be obtained. If it is connected to this 2, so this voltage is bypassed. So that means 1 less than that. Agree? If it is connected here, so 1 more less than that. These 2 are bypassed, right? Similarly, if it is connected here, so you have only VDC, and this is connected to this 5 point, this 5. So this A are 0. So that means you have 0 voltage. Clear? And a switch is connected between this point and this point. So that's supposed to block this voltage. If a switch is connected between this and this, so it's supposed to block, so this voltage, right? If a switch is connected between this and this, it's supposed to block, so this VDC. And for 4 and 5, if switch is connected, it's supposed to block this VDC. So that means all the switches are supposed to block VDC voltage, but the inverter voltage is so varying. It means in this particular case we have 4 VDC. So 4 VDC, 3 VDC, so 2 VDC here, so VDC and 0. So you are obtaining the 5 levels. It's clear? So what you understood that, so this waveform, right? So this is nowhere close to sine wave, right? So when compared to this, so this is slightly something like a sine wave, and this one is a more close approximation to a sine wave. So what exactly these multi-level inverters are? So it will aggregates the multiple small voltage levels like this. So multiple small voltage levels and synthesize a stepped waveform, and it will synthesizing a stepped waveform like this, right? So with a output of higher magnitudes, with the output of higher magnitudes. And another thing is that even though it is operating at higher voltages, the blocking device of these switches are less only. So this is operating for 4 VDC, but this voltage is VDC only. So that means if this voltage is, for example, 10 kV, and this is supposed to be 2500 volts only. So you no need to go for this 10 kV devices. Some medium or the matured medium voltage power semiconductors are enough. Okay. So this medium voltage, so power devices are enough to handle this voltage. And another thing is that, so this waveform is closer to a sine wave. So as this waveform is closer to a sine wave, so the filtering requirement is small. And sometimes you no need a filter. For example, this is feeding to a motor drive. So motor is having some inductance. So the inductance is itself is enough to suppress the higher order harmonics. Okay. So when the waveform is more close to a sine wave, so in that case the filtering requirement will be there is no filters are required. So this requires some filtering, and this requires maybe some filtering is required, and the waveform is more close to a sine wave or more close approximations to sine wave. So that means the filter requirement is not required, or the filters are not required. The thing is that, so why we are going for multi-level inverter? If that is the question, so that is to increase the power levels. Either direct power levels we can increase or increase the voltage handling of the inverter. So to increase the voltage handling and the power levels of the inverters, we are using multi-level inverters. What are the additional advantages with that? What are the additional advantages are? So that means the waveform, it will produce a waveform with low THD. It will produce a waveform, the output voltage waveform with low THD. That is one thing. And another thing is, it uses a medium power semiconductor devices. It uses medium power semiconductor devices. So that is another thing. So these are the additional advantages. The main things when why you are going for multi-level inverters is to increase the voltage handling and the power handling capability of a particular inverters. We are going for this multi-level inverters, right? So these are the advantages. So they can generate the high output voltage. So with matured medium power semiconductor technology with lower distortion. Okay. And they reduces the EMI effect and the filtering requirement. So this electromagnetic interference effect. So these switching inverters are so usually operated at switching frequency, maybe in the 10 kilohertz, 15 kilohertz, sometimes for the DC-DC converters. They're even operated at very high frequency, right? So in that case, if it is connected to nearby communication lines, that noise and the communication that frequency is usually in megahertz or gigahertz. So there will be some interference. So that is known as electromagnetic interference. So that interference can be reduced. And so they draw the input current with very low distortions. This waveform is drawing a sinusoidal waveform. So that means if this is connected to input, so this DC voltage is further obtained from AC source. So first we have AC to DC conversion is taking place from a front-end converter. That front-end converter is also multi-level inverter. So in that case, they draw input current with lower distortion, and it reduces the common mode voltage. So this common mode voltage, the voltage which is common to all phases, so that we will discuss in later classes. So what is common mode voltage? So how to reduce the common mode voltage, and what are the disadvantages of the common mode voltage, especially in case of machines, so that we will discuss. Okay, and they can operate with lower switching frequency. So in case of a two-level inverters, so no need to go for high frequency. All the switches are operated at high frequency. So in this case, so we can right. In this case, the switches will operate. For example, so in this particular case, right. So here, if you want 2 VDC only, so this particular switch will be turned on, right? So in this case, if you are only VDC only, this particular switch is turned on, right? So that means the switching instants are right, the whatever the frequency is there, so we can sharing between the switches. So therefore we have lower switching frequency, and they're fault tolerant and less prone to failure, and their cost is relatively low, right? So they're fault tolerant. So meaning is for example, some fault is occurring, right? Still we can operate this one. For example, this is faulty, this DC source is faulty. So instead of connecting this one, we can bypass this one and we can connect to some other or we can reconfigure the inverter so that it will be operate more or less its original condition. If it is not operating in its original, if it is not delivering its original power, maybe at reduced power, it may giving the output, right? So they're fault tolerant. So we'll discuss that. So how it is fault tolerant, and they're less prone to failure. So since we are operating with low voltages, so therefore the failure is also, there will be low chances of failure, and their cost is also relatively low. So when compared to high power two-level inverters, so their cost will be relatively low. So these are the advantages. So with this multi-level inverters. So in the next class, we had different basic multi-level inverter topologies, right? So we'll discuss in depth for all these topologies. So you have any questions in today's class?